Good morning, everyone. Myself Sharita from 4th BTech EEE, and our batch number is 5. Our project title is Intelligent Voltage Control in Distribution System by using upqc with fuzzy logic optimization. Our project guide is Dr. S. Suresh sir. Here are the contents. Abstract introduction, block diagram and working of upqc, integrating PI controller with upqc, and disadvantage of PI controller over fuzzy controller, block diagram and working of fuzzy logic controller, our simulation circuit and results of the simulation circuit. In modern power system, ensuring the delivery of high quality power supply to consumers has become increasingly critical due to the proliferation of sensitive electronic equipment and the rising demand for energy efficiency. The power quality issues that are estimated as voltage sags, swells, harmonics, and flicker can lead to equipment malfunction and productivity losses. To address these challenges, advanced power electronic devices have been developed, among which upqc stands out as a versatile solution. The introduction of upqc. UPQC is a unified and flexible device, and it combines the functionalities of both series and shunt active power filters connected back to back through a common DC link. And it can stabilize the voltage profile and reduces the harmonics and improves the power factor, and overall it can enhance the power quality. This is the block diagram of UPQC. Two power filters, that are series power filter and shunt active power filter, are connected to the distribution line. Series filter is connected in series with the line and is responsible for mitigating voltage related disturbances such as sags, swells and interruptions by injecting compensating voltages. Shunt filter is connected in parallel with the load, and it is designed to mitigate current related issues such as harmonics, reactive power compensation, and by injecting compensating currents. And this is the working of upqc. And integrating PI controller with upqc. PI controller, it can compute the error by comparing the actual and measured values with the desired reference value. The proportional component of the PI controller promptly responds to the existing error, and it can produce a control signal directly proportional to the current error. Meanwhile, the integral term integrates the error over time and aiding the elimination of any persistent error and contributing to overall stability of this power system. But in the place of PI controller, here we are using fuzzy controller because of the following disadvantages. The first one is difficulty in handling non-linearities, and PI control, as we know, PI controller is a linear controller. So to handle non-linearities, it becomes difficult, and it has limited adaptability to changing operating conditions, and due to its sensitivity and adaptability to human knowledge. Whereas the fuzzy controller can be used according to the human knowledge and can handle multivariable systems. So we are converting from PI controller to fuzzy controller. The significance of fuzzy controller lies in its ability to enhance the adaptability and robustness of the control system, and it can enable the UPQC to adjust its parameters dynamically based on real-time situations and load variations, and thus it can improve its performance. By incorporating fuzzy logic alongside with the PI controller, UPQC becomes more adept and handling the complex and nonlinear nature of power systems, and thus effective voltage regulation can be happen and power quality can be enhanced. This is the block diagram of fuzzy logic controller. First, we are giving crisp inputs. The fuzzifier will convert these crisp inputs to fuzzy sets through the process of fuzzification, and according to the rule base, the inference engine will analyze the input fuzzy set, and it generates the output fuzzy set. In the process, the defuzzifier will convert the fuzzy sets to crisp outputs through the process of defuzzification. This is the working of FLC. Fuzzification involves converting crisp input values to fuzzy sets using linguistic variables and membership functions. And during the inference, fuzzy rules are applied to the fuzzy sets and these are generated in the falsification stage. These rules define the relationship between the input variables and output actions, and by combining these rules, the controller generates fuzzy output sets. And finally, these fuzzy output sets are converted back to crisp output values. This is the fuzzy rule base we are using in this circuit. This is 7 by 7. NB indicates negative big, NM indicates negative medium, and NS indicates negative small. ZE means zero error, PS means positive small, PM means positive medium, and PB means positive big. This is the simulation circuit. These are the graphs without using upqc. That means at the grid side, voltage sag is observed from 0.9 to 1, and voltage swell is observed from 1.6 to 1.7, and harmonics are observed from 0.3 to 0.5. This is during the grid side, and by using upqc we can mitigate these voltage sag swells and harmonics at the output side. This is the grid voltage, load voltage, and injector voltage. Here if we can observe 0.3 to 0.5, we can observe harmonics, 0.9 to 1 voltage sag, and 1.6 to 1.7 voltage swell. Voltage sag is the reduction in the voltage value, and voltage swell means the increase in voltage value from 1 to 1.1 per unit, and the voltage sag is from 0.9 to 1 per unit. Here at the load voltage side, we can mitigate all these harmonics, voltage sag and swell, and the clear and sinusoidal output waveform can be obtained in the load voltage. And in the injected voltage, the upqc injects the voltage only during the disturbances, that is harmonics from 0.3 to 0.5, and sag during 0.9 to 1, and 1.6 to 1.7. It injects the voltage to mitigate the voltage swell. During the voltage sags and voltage swells, the series filter will will inject the voltage, and thus the grid voltage can be compensated and obtained as a load voltage. These are the references and conclusion. By integrating fuzzy logic controller with upqc, it emerges as a promising solution for intelligent voltage control in power systems, and the adaptive and robust nature of fuzzy logic combined with the compensatory capabilities of upqc, thus it can offer a viable strategy to address voltage related challenges, and it improves overall power system performance. And here are the results of the simulation circuit. This is the simulation circuit. Here is the grid. The transformers through series filter is connected through the transformers into the distribution line, and this is the shunt filter. Nonlinear load is connected, and to check the grid voltage, load voltage, and injected voltage, click on here. So as we can observe here, 0.3 to 0.5 can observe harmonics, 0.9 to 1 voltage sag, and 1.6 to 1.7 voltage swell, and these are compensated during the load voltage, and injected voltage is observed only during the disturbances. The magnitude of voltage and current can be observed here. As we are using upqc, the magnitude of voltage is constant. We have observed the voltage disturbances in the grid voltage side, but they are not reflecting in the output voltage side. So the voltage magnitude and as well as current magnitude are constant. As well as here we can see real power and reactive power. Real and reactive power are also constant, are also maintained constant because of using upqc. This is the DC link voltage. This is the DC link voltage. DC link voltage will stabilize the both series and shunt active power filters, and it can and it helps series and shunt active power filters to exchange the power and maintain constant and synchronism. This is the series filter. This is a shunt filter connected in shunt with the load. Thank you.